Okay, welcome. Good afternoon. Welcome to 240. So, first an important announcement. Who is going to go to ISSEC next week? What are you going to do? Okay, ISSEC stands for International Solid State Circuits Conference, and it's held annually, always in San Francisco in the Marriott Hotel. That's next to the Moscone Center, convenient part stop. And it's really the conference where things are happening in IC design. It's an IEEE conference. It has pretty good conditions for students to register, and if you have a research advisor, I'm sure that he will not only pay for your registration, but he actually will want you to go there, because you're going to learn there more than you can in class here, at least for that one day, right? So it's next week, Monday through Wednesday, and because of that, there will be no class Tuesday 1 week from today. Okay. So instead, I hope that more than half of you are going to be like me also in San Francisco that day. Okay. Yes.
I think that's the day the homework is due. So what should we do?
Oh, then we make it due 2 days later, right? Yeah. Or, yeah, I think the homework is small enough that you can finish it before going to ISSEC, but obviously you can't turn it in. So I don't think we need to extend so that you have time after ISSEC. It's not that big a deal, the homework, right? You haven't looked at it yet? Okay, well, look at it soon and tell me on Thursday if you have immense difficulty and so on, and you should do something else about it. Yes?
I did have one question about the homework. How close do our SPICE results have to be to the theoretical, like, unity gain frequency of 100 megahertz? Like, what percentage?
Well, kind of, it depends a little bit on the circuit. For simple circuits and in these examples, right, we are right on within a few percent, and very often you can tell right away what the difference is. Right, you didn't include the junction capacitance at the drain, and that adds a few percent to the actual load. Right, very often I also cook the examples. I put the huge load capacitor there, so it's kind of straightforward to estimate. You know what the load capacitance is, but of course there are additional elements that add a little bit to that. So as long as you're within a sort of a few percent and you can explain the discrepancy away right away, then I think that's good enough. I think the question almost is sort of upside down and offer a different view. Especially if you simulate a more complicated circuit than what we've looked at in the homework, at least so far, then of course you find lots of reasons why perhaps your result could deviate more from hand analysis. But then you will be even more interested in really knowing why the heck this is, because you might really be overlooking something and your design may just not be what you thought it ought to be. And so kind of perhaps almost the best way to look at it, we want SPICE to answer all of our questions, and usually when SPICE is too far away from what we think we should have, well, we can't get our answers, right? So then we have to figure out why the heck is it that we get the discrepancies, go and figure out what the most likely reasons are, include those in our models, and see whether that really explains what's going on. So that, I think, is sort of the general gist of also the homeworks, that once you've got your answers, your questions settled and so on, then I think you shouldn't spend time, right, to try to tweak digits after the comma. Yeah. It's really sort of a designer's point of view, right, like we are taking pretty much with everything in this course. There are other questions or suggestions? Okay, so we've started talking about noise. And specifically we talk about thermal noise, and we've talked about a number of things. We first talked about sort of the sources of noise and how to model noise in our devices, MOSFETs, resistors, and so on, right? Then we looked into how to calculate. And once we sort of know what the noise sources are, well, big deal, right? We want to know how does this affect whatever it is we're trying to build, right? And there first thing was output noise. So if we have a circuit with lots of elements in it, transistors and the like, then of course they're all going to have noise sources. There may be dozens or hundreds of those. What really matters in the end is how much of this noise makes it to the output of the circuit, right? And these calculations are fairly tedious, but they're kind of straightforward, right? We almost have a computer program to do it, and sometimes we have to play computer and just use that program. Then we looked at input referred noise. And that's really sort of a variation on the theme. Instead of saying how much noise comes out of the circuit, we model the noise of our entire circuit by how much noise do we have to stick into the input of a noiseless but otherwise equivalent circuit so that the output we get the same thing. And very often that's a very convenient metric, because if we have a sensor that produces, or a radio or whatnot, right, that produces a small signal, we can compare that then to the input referred noise of the amplifier so that we're going to use, and we can tell right away whether that noise is going to be a big problem, destroying our signal, or maybe not, right? Maybe it's okay, right? So it's a very convenient model. It's used consistently for all operation amplifiers. If you buy one, look up the data sheet, you'll find these numbers in there. Then last time we started talking about sampling noise. And I had introduced that in sort of a typical but somewhat narrow context of, I said, well, gee, we have some kind of a circuit, and it produces an analog signal. Then we put an A to D converter there, and really what's inside, the first thing the A to D converter does, or at least something the A to D converter is going to do, is it's going to look at the signal only once in a while, right? It may sample with 100 megahertz there, but that still means that once every 10 nanoseconds, it's actually going to look at the signal and convert the signal, and for the rest of the time, it doesn't even look at the signal. So now, what's going to happen is that the signal and also the noise are going to travel through this path, and let's assume that the A to D converter actually had a very high input impedance, so it really doesn't do anything. It's just model the entire A to D with this capacitor. Right? But then the signal and the noise are both going to end up on this capacitor. Now, when the noise is here, and then of course it's this broadband woozy kind of stuff on the scope. Once the noise is here, then it's a sample. It's a few microvolts, right? And whenever we open the switch, we can go with the voltmeter and figure out how many microvolts it was. It's going to be random, but it doesn't have any more this notion of sort of continuous change with time, right? And consequently, we somehow need to change our model on how to describe our noise. So the way we do that is we calculated what is the variance of the noise sample. Now, not as a function of frequency. What is the variance, the total variance of all these noise samples that we get there, right? Plus 3 microvolts, minus 7 microvolts, and so on and so forth. And we found that this was equal to KT over C. And that result we calculated under somewhat special circumstances. We said, well, when the switch here is closed, it's really some kind of a resistor OR. And we assumed that all the noise is coming from that resistor OR. Okay? And then, surprisingly enough, we found that the total noise, or the variance of that noise, the noise that we have on this capacitor here, of these noise samples on this capacitor, is not a function of the value of that OR, it's entirely a function of that C. Well, I've mentioned just a few sentences ago that this model is sort of, well, it's very practical, very often what actually happens. But in fact, this kind of a function that we sample a signal and we store it on a capacitor is used all over, not only for A to D conversion, but in general for signal processing, for analog signal processing with CMOS circuits. And the simple fact that you can grab a signal, store it on a capacitor, and then do something more later on, that's probably the one unique attribute that made it, combined of course with the cost and sort of the availability of CMOS, but that made it that for analog circuits, now CMOS has become the dominant technology, right? If you look at precision or so, stuff like that, then it's, or if you look just how much GM or how much efficiency can we get, well, bipolar or maybe even other more esoteric technologies, they always win. But it's this simple thing that with CMOS we can easily fetch a signal, we can store it onto a capacitor, and then we can do more computation with it. That turned out to be an extremely powerful thing that we can build that sort of compensates you for all sorts of otherwise deficiencies of CMOS. So anyways, this is very important structure, and we will see a little bit more, a lot more in 247, and we definitely want to know how to model the noise, right? Now, very often, and we're going to see examples for that also, the noise is actually not really coming, or not all the noise anyways is coming from this resistor, but this is an amplifier. It also has noise, and the noise from the amplifier really is making it to this capacitor. In that case, the equation, interesting enough, looks almost the same. And we'll see examples of that, plenty of examples of that. The equation looks almost the same with the exception that this equation is multiplied by a factor that I usually call NF, noise factor. And depending, for example, on how this amplifier is built, this noise factor can be equal to 1, or bigger than 1, or less than 1. I can tell you most of the time it's bigger than 1, unfortunately, right? But we'll talk about how to of course go about what is affecting the magnitude of how big this NF is. And the key thing is, again, the noise really has this form cation C. Very profound, very important result that we're going to use all over, right? Sort of combination of cation C with noise factor tells us a lot about the noise in our circuit. Okay. Now I would like to revisit the issue of spectrum a little bit. And, well, if we have this sample and hold circuit, and let's look at only the noise, right? So it's just the noise from this resistor that ends up on this capacitor. Then we, of course, know the spectrum of the noise from the resistor, right? The spectrum of the noise from the resistor is white for practical purpose, right? We also know the spectrum of the noise as it appears across the capacitor. Well, that's simply the noise from the resistor filtered by this low pass filter, and consequently it's going to look like this, right? So that's the spectrum of the noise on the capacitor, right? So actually, if I haven't said that, then I say now that the original thermal noise sources from a resistor or a diode or a BJT or MOSFET or so, they are white. But once the circuit acts on that noise, the noise is not necessarily white at all, right? So, so here in this case, it has this low-pass characteristic simply because the filters, the noise sort of filters, the circuit filters its own noise and gives it the characteristics of the circuit. Okay, so we know that. So while the switch is closed, the spectrum of the signal here is continuous, and it has this form. Now, Now, question. The A to D converter, if we go back to the A to D converter, is going to convert the signal and also the noise. And it's going to convert. Let's for a moment make the signal 0, right? We'll use this superposition so we can really deal with one thing at a time. So we'll talk only about noise. So the A to D converter now is going to convert these random noise samples. What is the spectrum of those are going to be? Right? If you, let's say this A to D converter is hooked up to MATLAB and you can type FFT and it gives you a spectrum, what is that going to be like? Well, first, it's a sampled signal now, and so the spectrum is kind of repetitive, or it's defined only from 0 to fs/2, right? And beyond that, it's really always the same, right? So that certainly, for one, is going to happen. But between 0 and fs/2, what is the spectrum going to look like? Well, for that, we need to understand how those noise samples were generated. They were generated from a signal that had this spectrum, the red one here, right? And then this thing was sampled. And because of the sampling, all of the noise that was at high frequencies here folded down to lower frequency. Well, so what the spectrum here is going to look like depends on the sampling frequency. If we sample somewhere like here, well, I made this already, fs/2, then that means we sort of retain this, what we had already, and we take this one, we flip it around and put it on top here. We take this one, we don't flip it around, we just ship it on top here. But we then take this sliver here, we flip it around again and put it on top here. Well, this noise here was white. This one's also pretty much white, right? This one here was this triangle. Here was a triangle also, but the triangle looks the other way around once we flip it, right, because of the aliasing, right? And so on. How is the thing going to look like when we stack up all these triangles that look all sorts of different directions? Well, it turns out, and you can try this or you can throw math at it, but it turns out that it looks pretty much white. For all practical purpose, in fact, it really looks white. Okay. Another extreme would be, let's say we sample with this frequency, make this fs/2 now in our second sort of thought experiment. Now, this thing stays put. Right? Then the next sliver here with the triangle gets flipped around and is added here. And then another triangle that doesn't get flipped around is added here. What do you think the end result is going to be? Sort of roughly, the spectrum of the end result is going to be. Well, in the end, we are going to have a spectrum that pretty much looks just like our red shape here. Why? Because the power of this stuff down here, remember, this is really a log scale, otherwise this wouldn't look like this. Right? The power of this stuff is so low that it really doesn't change the shape here very much. So if we oversample this noise, well, we're going to see some kind of a low-pass characteristic in the sampled noise also. If on the other hand we undersample the noise, this case here, then we're going to see white noise. Okay. So then we have to ask ourselves the question, well, what are we going to do? What do you think? Well, I can tell you. Most of the time, almost always, we're going to be in this situation when we are here, then there is something terribly wrong. Why? Well, because most of the time, this thing is going to, right, there is an amplifier, of course, also that produces a signal here, and we want to catch that signal onto a capacitor. Well, we want to catch it faithfully. In other words, we want that the signal really has time to settle to its correct value on this capacitor. That means that this RC thing has to be very fast. In other words, it's got to have a time constant that is way out there, right? It's way faster. So in other words, this 1 over this is the time constant of the circuit, right? That better at high frequency compared to a sampling clock period. Okay? So most of the time we're going to be in this situation here. And then the noise really is white. Okay? So sampled noise can have a very complicated spectrum, but in practice, on the most reasonable circumstances, how we're going to use these circuits most of the time, and all the time that I've used them so far, unless I made a mistake, right? The noise is pretty much white. Okay? There is one exception, and that is if here, of course, we had 1 over F noise, then now you need to use your microscope because my F is too small. Then this 1 over F noise was down here, right? There's a little sliver down here. Well, there is just no aliasing happening with that at all, and so that just plain shows up. Shows up here again, right? So narrowband effects, such as 1 over F noise, or the signal for that matter, which ultimately is going to be in the picture, better don't alias, right? Sure. But for what the broadband white noise is concerned, under reasonable circumstances, generally it is white. And I have a student in my group. I have lots of extremely bright students in my group, and I asked him this question, and he pulled out an amount of mass that just leaves me in the dust, but it's here in case you are so inclined. He calculated what the spectrum of this noise is as a function of the ratio between the sampling frequency and this pole frequency here that he called some kind of a tau, T over tau ratio. Right? And typically this T over tau ratio is something like 6 to 10, depending on the precision. If you want to be accurate to 10 bits, to 16 bits or so, then this ratio is 10 to 12. If we only, and we will calculate that later. If we only need to be accurate to 8 bits or so, then maybe that ratio is 5 or so. Well, already if the ratio is only 3, this, if you can use just a little bit more zoom for just this diagram. Thank you. Then the red curve. Then, I mean, this is within half a dB. That's kind of the question. I mean, how much should we bang on SPICE to get a good agreement? Right? If you know the noise of your system to within a couple of percent, you're done, right? Why? For example, the temperature changes a little bit. Well, that changes your noise by more than a couple of percent. Right? So we really can't cut it with noise to 3 digits after the comma. Okay, if we didn't oversample, well, then the spectrum isn't white. But again, I mean, this blue case, well, find a reason why you would want to do this. Okay? So that's the spectrum of noise and also the spectrum of sampled noise. In the end, it turns out everything's simple. It's kind of white, right? And sometimes it's really important to know that also. But really, why is it so? Well, it's not so straightforward. So I hope, make sure that you understand that. And if you have questions, ask them now or during the office hour or whatnot. Okay, now the next few slides I want to go over a little bit quickly. Those are mainly kind of placeholders. Suppose you do a PhD thesis or go out and work for a company and you build a complicated circuit, and of course it has lots of these switches and they sample noise and so on, and you want to know what is the noise from this circuit. Now, if you've already done the homework and you did the dot noise analysis, then you know that dot noise analysis is really some kind of a special form of an AC analysis. And an AC analysis, well, just couldn't care less about switches, right? It assumes that the circuit has one configuration, that is it, and you can't turn on and off these switches. Okay, so it's kind of difficult to do a complete analysis of this sampling noise, right? More recent versions of SPICE, in particular the one called Spectre, they have features built in that actually allow it to measure periodic noise. And I show here an example on how to do that, and I list the commands that you have to type into Spectre, kind of as with two goals. One of them, I would like to alert you that you're not totally out of luck if you need to simulate and verify a circuit that uses sampling and its noise performance. And secondly, also to give you kind of a point on how to do that. There is also a comment here. The author of this program, Spectre, Ken Condit, when he saw my slides and so on, he said, well, why do you do it so complicated? There's a more clever way to do it in my simulator. Well, I haven't had the time yet to try out a clever way, but I put the note in case you have time. Let me know if you can verify that that works. Okay. So then I did here, again, I really want to go here quickly through this. I did do a couple of examples. I did do here an example where I actually sampled my noise, but I oversampled the noise. So the case that is kind of, I said that in practice doesn't happen. I only did this because I wanted to verify that the simulator actually is able to give me the right result, and I sort of felt, well, if I make a more complicated curve, so then it has to work harder, and it's going to be less easy to, by sheer luck, to produce the right result, right? So I did that. Now, originally the noise out of the simulator comes out in sort of a strange form. Then you have to undo what I call here sync distortion, and so then the noise, this oversampled noise is going to be this. Here is a linear scale. It's going to be a low pass. Here is Fs over 2. And then it's going to be just a mirror, again, to Fs, and from then on it's just going to mirror around that. Now, we know that the power of this noise is going to be equal to Kt on C. And the noise power is integrated from 0 to Fs over 2, right? So I did this experiment with a 1 picofarad capacitor, and then I integrated. And I wanted to just know, well, how accurate is SPICE in predicting that? So here is the result. Instead of plotting just the integral, I normalized the integral with Kt on C, where C was the 1 picofarad capacitor, right? And so this at Fs over 2 should be just 1, and lo and behold, it's 0.4% larger, and so by the argument that we used earlier, I'm happy with that, right? Sort of. And then SPICE is even good enough that if I double the integration interval, then of course the noise power doubles, but then I take the square root to get into the microvolt RMS scale, so I get a square root of 2 increase, and this is a way to calculate some approximation the value of square root of 2. Maybe you have other ways, but sort of a circuit designer's approach is pretty interesting how to calculate it. And then up here, we have quadrupled the noise bandwidth, and lo and behold, the noise now is also square root of 4, 2 times bigger. So apparently, this SPICE simulation actually does work. It gives the right result. One of the reasons why it's important to figure that out is, first of all, always, if I use something new in SPICE, usually I do not type in quite the right commands, and also here you've seen that I used a more complicated way to do things than the author of the tool told me. But the other thing is there are all these parameters that you have to stick in. Heck, what parameter values do you need? Well, beats me. What is it in the first place? Mux sideband? Well, whatever. Right. So I wanted to be sure that I can get the right result, and very often I make up some simple kind of a test circuit where I know the result from the start. I run that through, and when I'm confident that is working, then sort of I try it on the big stuff, right? Okay. Trying it first on the big stuff very often is a big waste of time, because it's not going to work, and then you have a big problem on your hand to debug, right? You don't want to do Okay, so sampling noise. Next topic. Now we're gonna look at a few more examples, but very importantly also we're gonna look at yet another other way on how can we quantify noise and put it in perspective with what are going to be ultimately our design parameters. And for that we'll start by looking at the signal-to-noise ratio, SNR. So signal-to-noise ratios has all sorts of applications. Basically the ratio between the signal power and the noise power, and of course there are all sorts of things that you can put in for the signal and for the noise, and here obviously we are going to put the thermal noise in for the noise part. So this SNR, it's really defined, if you want, as P signal over P noise. Okay? And so we need to figure out what is the signal power. Well, that's really the amplitude of our signal, at the 0 to peak amplitude of our signal times 1/2, because we want to get the RMS power, right? Okay. So then we have the noise power, and we know now that this noise power is kT on C, some salient capacitors in our circuit. Up to now, it always was the load capacitor. We'll see that it can be other capacitors also later on, times NF. And that NF, again, if sort of 1 is a good thing to strive for, less than 1 is if you are really aggressive and you're going to have a hard time there, and larger than 1 is often a fact of life, right? So the signal-to-noise ratio consequently is equal to 1/2 times V signal square times kT times C. So if we want to have high signal-to-noise ratio, then we want to have large C. In particular, the signal-to-noise ratio then is measured in dB, and I guess I can use my slide here. So I plugged in here a signal that is 1 volt peak to peak, right? Has this power. Noise, I use a 1 picofarad capacitor, 64 microvolts RMS noise. And then I calculated a signal-to-noise ratio, and I converted the result to dB, and found that you get, like, for example, 80 some dB, whatever, a number. Now, if I wanted to double my signal-to-noise ratio, doubling means I have to increase in the log scale, means that I increase by 6 dB. Then I have to I want to increase the signal-to-noise ratio by 6 dB. That means that the power ratio goes up by a factor of 4, and the RMS voltage ratio goes up by a factor of 2. Right? So my signal now is twice as large compared to, in volts, compared to the noise as it was before. So that means that either I have to increase this by a factor of 4, double the signal voltage, or alternatively I have to decrease this one by a factor of 4. That means quadrupling C. Right? So for an additional 6 dB, I need to quadruple the value of C. Now let's put some meaning into this dB stuff. And the best metric is to relate dBs to bits. I think we briefly mentioned that before. If in a computer we represent a number with a finite number of bits, let's say 16 bits, then we cannot represent the exact value, perhaps, that we want to store, but we instead make a quantization error. Right? We have to quantize to the round to the nearest integer that can be represented with just 16 bits. That makes an error. Well, that's another form of noise. Not thermal noise at all. It's quantization noise, but noise. And turns out we can also measure it by a variance, right? And now we again can calculate a signal-to-noise ratio. And now we can relate relate that signal-to-noise ratio to bits. What I did here is the signal power is simply delta. Delta is the amplitude of my LSB. It's the size of my LSB. Okay, so how big a signal can I represent? Well, the entire range is 2 to the n times delta to the n minus 1 times delta, right? That's the entire range that I can represent with an n-bit number. Right? Now, the 0 to peak value is half of that, and the RMS power is this square times 1/2. So that's what we had here. And then the noise part is this delta square over 12. I take the ratio, and that's written down here. And now we can, and if we can use a little more zoom here on this table here, we can relate number of bits to dB. Yeah, a little bit more zoom, please. Well, I guess it is again. Okay. So 8 bits correspond to about 50 dB. 98 or give or take 100 dB correspond to 16 bits. 24 bits correspond to 140 some dB. Now, if you sort of looked at data sheets or no audio equipment or so, then stuff crops out around 100 dB or so. So that analog circuits, they sort of good ones get into the 16-bit equivalent signal-to-noise ratio range, and far beyond that is hard, and 8 bits, sort of 50 dB isn't that big a deal. But of course, I mean, there are miles difference between 50 and 100 dB because we have a logarithmic scale. Right? Okay, another thing that is kind of buried in this equation, and that is really important here, is that for every bit I add, I get an additional 6 dB of signal-to-noise ratio. Okay, so that makes now sense. That's why this example from before. An additional 6 dB of signal-to-noise ratio means that I improve my equivalent signal-to-noise ratio by 1 bit. So if I have a circuit that produces accuracy, and so noise-limited accuracy to, let's say, 15 bits, and I really want 16 bits, maybe I have to do other things, but one thing I'm going to have to do is I have to increase my capacitor by 4x. Okay, so now we can put this thing together and relate it to power. So 1 bit apparently corresponds to 6 dB, or 4x in the power signal-to-noise ratio. That corresponds to increasing my capacitor by 4x. Now, the circuit, the bandwidth of my circuit, the speed with which we can operate is proportional to Gm over C. Right? Consequently, if I want this extra bit, but I don't want to go any slower, what do I need to do to Gm? Well, I need to increase that also by a factor of 4. You know this? Yeah, I asked your neighbor. You knew this already? Okay. Okay, so I have to increase Gm by a factor of 4. Well, if I now this V star business again comes in handy, right? V star is 2ID over Gm, right? So if I want to keep V star the same, I increase Gm by 4x. I gotta increase ID by 4x. So without really getting deep into figuring out what transistors, what even circuit we want to use, we know an extra bit is going to cost us a factor of 4 in ID, also a factor of 4 in W. That's probably less consequence. But a factor of 4 in ID, that's 4x in power. Very important result, right? It says that, you know, if we build a digital processor, actually I never built one, but people are kind of generous, right? They jump from 32 bits to 64 bits. They don't even consider to stopping somewhere in the middle. Somehow not worth it, right? In analog circuits, it's very different. Sure, we are going to stop in the middle. We are going to stop in the middle of bits. If you need to build an A to D converter or a circuit or whatever, a function, that needs a signal-to-noise ratio that corresponds to 12.5 bits, right? It's just 12.5 times 6 dB plus 1.7, right? Then you're going to build a circuit that has that 12.5 bit equivalent resolution, not 13 bits or 14 bits or so, and certainly not 16 bits. Right? Why? Well, because you're going to pay for all the extra resolution. You're not going to get anything for it except for a really hot circuit and a dead battery, right? So every additional bit quadruples power dissipation. And so I mean, to put this into perspective, let's suppose that you've designed a 15-bit A to D converter, and the marketing guy comes around and says, hey, look, I mean, this is wonderful what you did, but my customer, and it dissipates only 100 milliwatts, that's so wonderful. My customer really just wants one additional bit, and I'm going to sell 10 million to him. And the power, 100 milliwatts is just fine. And you tell him, well, sorry, but now the power is going to be larger, about 400 milliwatts. The salesman probably is going to not have a very good day, but heck, this is physics, right? Too bad. Over-design is extremely costly. You don't throw around dB. Something very important to know. I say that because I've seen people who say, well, I got to build a 12-bit A to D converter just to be on the safe side. I design a 13-bit A to D converter. Maybe I get 12 bits. Well, first of all, I think that approach is flawed. That says, well, basically, I don't know how to build an A to D converter that has any given spec, and consequently, I just try something, right? But secondly, over-design is not permitted. Now, I should put this into a little bit of perspective, and that is, in practice, of course, the power consumption comes from a lot of things. Right? In your A to D converter, of course, you have this amplifier that amplifies the signal, and its power dissipation really goes up 4x if you add another bit. Right? But then there is other stuff like the biasing network, clocking networks, the reference network, and there the power dissipation may not go up at all or only very incrementally. So in practice, usually adding an extra bit doesn't really add increase power dissipation by 4x. It's somewhere between 1x and 4x. Right? Also, this problem really happens for noise-constrained circuit. Right? If you build a circuit that needs only 3 or 4-bit resolution, well, you can't make a transistor that has a width of only 5 nanometers. So you just can't make it, right? You need to make it wider, and so or you can't make capacitors that are only half a femtofarad. They're going to be larger, right? So sometimes you're not limited by noise. You're limited by just sheer size. You can't make stuff that small. Obviously, that is going to become less and less a problem because increasingly we can make stuff ridiculously small. When I was doing my thesis, then using half a picofarad was kind of a small capacitor. Now 50 femtofarads, well, is a comfortably big capacitor, right? And sometimes, of course, you have to make components somewhat larger to get matching, right? If you want 2 capacitors or 2 transistors to be ratioed exactly 1-to-1, well, if you make them very small, then random variations are going to make that ratio very inaccurate, right? So take this very serious, but with a grain of salt, right? Don't already fill out your data sheet power number. You probably can do somewhat better than that because this wasn't totally noise limited. Okay. Now again, before even starting to design circuits, you want to use this for a little bit more. Just how good circuits can we build in the first place? Huh? Very important. If you embark on a new project, you want to know whether you're going to succeed, whether you can actually meet those goals with reasonable other metrics like power or whatnot, right? And you probably want to do that before you have spent 1 year designing amplifiers and so on, you find out in the end that, well, I just didn't find a way to do it, and why not? I'm not even sure. Well, okay, so here the question what we are asking is, we build an analog circuit, and we want to build we want to get the highest number of dB or the highest number of equivalent bits out. What is sort of reasonable to ask for? 200 dB, 20 bits, right? Or something a little bit more modest. Right, so for that again we have the signal. The best thing we possibly can do is we have a signal that with amplitude that spans the entire supply. You're going to be hard pressed to do better than that, right? So the noise. We've talked a lot about this one. Ratio gives us signal to noise ratio. Now we have the signal to noise ratio again in dB, but we have it now as a function of supply voltage. Well, we know already that's kind of sort of bad news, right? Supply voltage is going to go down. We have it as a function of capacitance. Well, capacitance, well, that's kind of our hope that it will go up, right? We figure out better ways to make large capacitor in small size. And we have this noise factor. We're going to be generous on the next page. We just assume that this was 1. Right? Then we can use this equation now. Let's assume a generous 3 volt supply voltage. And let's assume that we have 1 nanofarad available to make our capacitor. That's kind of pushing. That's a big thing. That's going to be costly. Well, that translates into 110 dB, and if you use the equivalence between dB and bits, that's on the order of 18 bits. Okay. So in an IC, you can't get a whole lot more than 18 bits, and even 18 bits are going to be very, very, very hard, and most of the time to get it. Because this is a little bit generous assumptions here. On a PC board, we can do better, right? We can increase the supply voltage probably 10x or so. And of course, we can use relatively much larger capacitors. There we can get to sort of 140 dB, 23, 24 bits kind of numbers. So actually, I mean, everybody wants to integrate. Well, it's not always the best thing. If top signal to noise ratio matters, I'm going to buy one of these old-fashioned operation amplifiers from Burr Brown or ADI or Linear Technology or so, right? Use a 30 volt supply, buy the biggest and best capacitor, and we're going to beat the IC design. Of course, it's going to be bigger and probably more expensive. It all depends what matters, right? So here is a little note, and you may see data sheets that actually claim for A to D converters or so that actually claim more than 18 bits. And there are 2 reasons why they do that. There is, first of all, there is the one that lie. Don't believe everything that's in a data sheet. There's plenty of the ones that lie. For example, in A to D converters, it's common to just count the number of pins on the package and say, it's got 16 pins. It's got to be a 16-bit A to D converter. Well, we know it doesn't work that way, right? 16 pins worth of noise, right? Okay. So, but then there is another legitimate case where you actually can do better, and that's oversampling. I don't really want to go into that, but the basic concept is that you have your signal source, and you build your A to D converter, and you spit thermal noise into this thing on the order of, let's say, to the tune of like 18 bits. And you sample this thing at something like, let's say 4 megahertz. Then out here comes thermal noise that goes from 0 to 2 megahertz. Now, we've argued before that the spectrum of this thermal noise is going to be approximately white, right? Let's assume that the A to D converter has many bits. We don't care, right? The quantization error is negligible. Right? We are just concerned that despite all the good quantization, we still have thermal noise, and if it swamps out the LSB, then we still don't have our 20-bit A to D. Well, let's try to get an additional bit for this thing. Well, if we want to get an additional bit, we have to cut the noise power by 4x, right? Okay, so we have to somehow slice this down into 4x. Well, we make 4 slices, and this is the only slice, for example, that we keep, right? Okay. How do you do that? Well, it's very simple. We put here a low-pass filter. And that low-pass filter filters everything out that is above 0.5 megahertz, right? It filters away all the noise, so it filters these 3 slices of noise away. Now the noise is down. But of course, it also does away with any signal that was up at these higher frequencies. So we kind of trade bandwidth for noise. So there is no miracle, right? We haven't really done. But sometimes what this does, right, is instead of building here a bloody, incredibly huge capacitor, we use a smaller capacitor, run our circuit real fast, then we use a digital processor called low-pass filter here that sort of has noise gain, right, to use an RF parlance speaking, processing gain, right, that removes all of this extra bandwidth that we had here by running this fast for no real reason except for this noise, because our signal had only 500 kilohertz bandwidth, say, and then we pocket the extra bits in terms of signal to thermal noise performance. So that's one way. That's a way to get around it, but that's about the only one I know. It's safe then. Nice 30-volt op-amp. Okay. It's good to know these things because before you start your startup company, you know already where to put the stakes so that you're actually going to succeed. Okay. Are there questions about that? Comments? Anybody has a good story? Yeah. $36, yes. No, the signal didn't increase. The idea is only the idea that we need to generate enough GM, right? The signal power was simply limited by the supply voltage, right? It was VDD squared times some factor, right? So increasing the current that we drain from the supply hasn't increased our signal power. It could be different if we somehow use the current mode circuit where the signal itself is not represented by a voltage but by a current instead. Well, then it could be different. Now, then the whole rest of this story is a little bit different too, right? You can't store a current on a capacitor. You would have to use an inductor there. And heck, that kind of gives me an idea. That would be a nice homework or maybe a nice midterm exam or something like that. There ought to be. Who is working with squids? Nobody, right? It's somehow died. But I kind of wonder, people working with squids, they must have exactly the same laws, except that the whole thing is current, right, instead of voltage. So no, it's unfortunately get only a factor of 4. Does it make sense what I said? No, sorry. So, yeah.
I had a question about slide 34.
Let's answer his question. Handle it first. Yeah. Did it make sense or not? let me. Do you want to rephrase your question, or sort of what's not clear, or should I try to just explain it again? Okay. So the signal power is proportional to V signal square over 8 or something like that, right? Some factor. So by increasing ID, we really didn't change this at all, right? And all we really changed was the noise power because C went up. And yeah, I guess perhaps the reason why you get confused here is that we measure power in volts, and the power and the reason why we do that is that the noise and the signal, they all appear on the same load resistor, so it kind of divides out and doesn't matter, right? So, but because of this thing here, because this factor doesn't change, we really get only the factor of 4. That's the only thing. Okay? Yes, now. Yeah. 34, you said.
Yeah, the bottom of 34.
Okay.
You mentioned there that at the bottom it says signal noise ratio goes up by 6 dB, and that's the voltage signal and noise ratio?
Yes.
So sometimes you're talking about a power signal and noise ratio, and sometimes a voltage signal and noise ratio. Do they specify that usually? Or?
No. The signal to noise ratio is always calculated as the ratio of power. It's the ratio of powers, but then when you go to the dB scale, then we use 10 times log 10 of that ratio, right? But very often, as circuit designers, we actually don't deal with this volt square business or watts or whatnot. We actually look at volt RMS, and the volt RMS thing is the square root of the power thing, and so consequently, in that case, if we want to have the RMS thing or volts, right? If we want our LSB be down by a factor of 2 in order to have an extra bit in our A to D converter, then it's really, we're talking about the voltage ratio that improved by a factor of 2. That means that and now 20 times log 10 of 2, of course, is 6 dB, right? But that means that the power ratio, the volt square ratio, had to change by a factor of 2 squared or 4. Yeah. It's always, yeah, I mean, it's the old question, right? Whenever you use dB, you have to multiply with 10 or with 20, one or the other. Well, which one? You got to look at the units. Which one you need to do? Okay. Clear enough? We can go to the next step. All right. So noise and feedback. First is kind of a summary, and afterwards there is all sorts of examples where we actually go and verify what the heck we are saying here. First of all, if we have ideal feedback, and I will show more exactly what the heck I mean with ideal feedback. If we have ideal feedback without sort of second-order effects, then the input referred noise of our circuit doesn't change because of the feedback. At the output, of course, usually the noise changes. The minute we use feedback, well, we change the gain of our system, and consequently the noise gain is also changed, so we get more or less gain, right? I mean, if we leave the amplifier open loop, it may have a gain of 1,000. We get more noise out, but we presumably also get more signal out. If we use feedback, we reduce the gain both for the noise and also for the signal. And input referred, there really hasn't been any change. Another way to say is that the signal to noise ratio really hasn't changed. Okay. In the ideal case, feedback doesn't change the picture of noise. Okay. That's only the ideal case, though. In practice, feedback actually usually increases the noise. First of all, we suddenly have a feedback network. Heck, I mean, I think I mentioned it already once before. You add a device to your circuit, and it may do a few good things, but it's also an additional new noise source, and for noise it may do bad things. In the end, you may still win. The benefits may win out, but so noise from the feedback network we have now in addition. And then there is this kind of bizarre thing that I don't really want to explain now, but that's going to be really the killer. That somehow, depending on how we actually use our feedback network, it may be that the noise, unfortunately, is amplified by a larger factor than the signal. And then the feedback network very well can lower our signal-to-noise ratio. And unfortunately, that happens often. And we will look at when and how this happens. So this is only the summary. When you get confused, you go back to this, or when you fall asleep. Now, you go back to this later and look at this. What the heck you should have heard and understood if you hadn't fallen asleep. Okay, there is a third point, and that is sort of the PhD point. Sometimes you can be really clever about this stuff. And so sometimes it's actually possible to just feedback enables you to build a circuit. To build a circuit that has low noise, but that would be totally impractical without feedback. A student of mine got his PhD for just that thing. So what he did was he built an accelerometer. That accelerometer that I had way in the very first lecture. You see, I like this thing, and I have reasons. So what an accelerometer is basically like this table. If there was an earthquake now, this table would jump up and down, and we could measure the magnitude of the earthquake by looking at just how far it jumped up with respect to the floor, right? Okay, the accelerometer that guy built was a little bit smaller. It was just a sliver of polysilicon. Now, the problem he had was that that thing bounced down even when there wasn't an earthquake. It just bounced down, up and down, because air molecules constantly crashed into that thing, and because that sliver of polysilicon is light. That sliver of polysilicon bounced all around just because of the air crashing into it. Okay? No wind. I mean, it was packaged and so on. Just the thermal agitation of air molecules. Okay, so what do? Well, you get rid of the air, put this in a vacuum. Fine. But now you have a totally underdamped system, right? You put this, if now an earthquake happens, then the thing gonna respond to the earthquake, but then it's gonna ring like this forever. Totally impractical system. You've gotten rid of this noise problem due to the air molecules, but you have now a system that, well, you can't use it anymore. Right? Now, of course, if you introduce feedback, you can stabilize these oscillations. And then you have the low noise, and you got rid of the oscillations. You suddenly have built a system that actually has less noise. But it wasn't really because of the feedback. It was because of the air molecules that were away, and the feedback made it possible to use that system. Okay? So if you want to get a PhD, then this is probably a good category in. If you just want to build good circuits, then it's probably good to know about these. So we're going to focus on these 2 points here. Okay? Okay, so I mentioned something about ideal feedback. So here is what I mean by ideal feedback. We have an amplifier. We've calculated its input-preferred noise, and we apply feedback around it like this, right? Sort of like MATLAB simulator kind of approach. Well, the feedback really just gets added to the input of the amplifier, or we could actually represent this as just get rid of this thing and just add the noise to zero. It would be the same thing. And then it's a simple step to just move the feedback noise out here. What's the input preferred noise of the amplifier without feedback? Well, it's Vn, right? That was our definition. What's the input preferred noise of the amplifier with feedback? Well, it's Vn. So the input preferred noise didn't change at all because of the feedback. Ideal feedback, no change in noise, as promised, right? So that was our first premise. Then I said, caveat, be careful. Real feedback networks, They may add noise. And now we do that. Here we have a real feedback network, these two resistors. Here, these are the noise sources from the feedback resistors. And now, the calculation that I'm doing here is exactly that stupid program that we looked at, I guess, last lecture. Very tedious and very long, and I wrote only about half of the equations here. But basically, I'm calculating the gain from every noise source, and also the input, incidentally, to the output, right? And then I also calculate the gain from the input to the output, and I divide my noise gains by that, and therefore calculate the input referred noise. Okay? So the input referred noise, then if you can use a little bit more zoom, please, is first of all the noise from the amplifier. I mean, it sticks here, obviously, right? That's the amplifier noise, no change there. And then I also get the noise from these resistors, and I simplify this a little bit. You can go through these calculations yourself, not very difficult, but do it just to have yet another example on how to calculate noise. It's easier to do it now than during the midterm. And so you have an expression here. It depends on the value of the resistor, and also it depends on the gain. Well, apparently, even though we are looking input referred, if I want to make a high gain amplifier, so then I still get a little bit of extra noise. Whatever. This factor here is approximately equal to AV0. Right? Okay, and then I made an example here, kind of trivial. But the point is of course that now I really get extra noise from the feedback networks. I guess presumably what I normally will want to do is I want to make this term here, the noise from my feedback network, small compared to this noise here, the noise from my amplifier. That way the feedback kind of doesn't cost me noise-wise, right? Now, if you look at this equation, AV, presume, is given by the application. So if I want to make this small, I have to make R0 small enough. Well, of course I can make, R0 is just the proportionality factor for these R1 and R2. So of course I always can make R0 small, but the smaller I make it, the more current from my amplifier now flows into my feedback network. Very common problem. You're going to see that all the time. Yeah, we can make the noise small, but we need to make these sucker resistors tiny small. And then go and drive these, right? Now you need a bigger amplifier to drive this garbage. Well, fortunately, it's Boltzmann that's stuck in there. The guy in the next cubicle or in your competitor's company, he has exactly the same problem, except that he probably doesn't understand it, and so you're one better. All right, so noise from the feedback network cannot be ignored. Now, we just have another 10 minutes, and that gets me to that point in my summary slide where I said, well, sometimes because of different gains and so on, I can get a lot of excess noise. And so here is again shown a feedback amplifier. So here is the signal source, which in this case actually is a current, right? Sure, we can do processing with currents. And here is the noise, which I model here also with a current, with a current, right? And of course, I mean, changing R or so doesn't change the input referred noise. I mean, the input referred noise in this circuit, it's trivial to calculate. It's just equal to IN squared, right? Because IN and the source are just parallel next to one another. Right? The same thing. Right? Okay, so feedback really has no impact on noise here. And in this example, incidentally, I ignored the noise from the noise resistor because I'm only interested now. I know already that the feedback network gives me extra noise, and I trust that you will go through the example and make on the previous page and understand and make sure you can calculate that. So in practice, of course, you cannot ignore that. Incidentally, here it's very simple to analyze this. The best way to analyze this is here I would now represent the noise from this resistor, not by a noise voltage source, but a noise current source. So, okay. And then I would split this into the noise stuck into this terminal and the noise stuck into that terminal. Okay, so I make, so this would be INR square. I get rid of this. And then I have also over here, now a little bit less zoom, please. Oh, that's a little bit too much. Okay. I wish I had that button. It would be so much simpler. Okay, so now I kind of, instead of having just one noise source, I have two. Looks like a bad deal, right? Well, but this here is an amplifier that has a voltage output here, so the impedance here is very low, or 0 if the amplifier is ideal. So this thing is really shorted out, so I don't need to consider this one. But this one here, I see right away it just adds to the input referred noise of my circuit, right? So I didn't have to calculate anything. I just sort of thought it through. So that's something that sometimes you can do that. You sort of, just by inspection of the circuit, you can understand how noise will affect it. And the more you get experience and so on, the more you will do that. For that, incidentally, I guess sort of would like to sort of make a point that the homeworks, most of the homeworks that I give you, they are actually rigged. Rigged in the sense that once you've calculated the thing, there is a message hidden in there. Right? And so once you've calculated the result from the homework, don't just sort of sigh of relief, finally done with this one, next thing. Right? But look at the result. Try to figure out what it actually means. Whether there isn't a quicker way or a more intuitive way to explain what it is. Several interesting and more or less profound things about circuit design are hidden in those results. And if you try to get them out, or sometimes they're also just written up in the solution, of course, from there too, and then you got something for your hard work, right? Anyway, so here also, if you, obviously, right, if you had gone and calculated this, let's say, with voltage noise and done all the calculation, then got an equation for the input referred noise, you would have seen from the format of the input referred current noise that it's really just a noise from that resistor. Then go back if you see something like that. Look at the circuit and see whether you don't find a way to more quickly calculate it, like what we just looked at, right? Okay, so now we have the same inverting amplifier, but this time we've got a voltage input and not a current input. And the feedback network now includes two resistors, but technically speaking, really, this is if you use Gray and Meyer terminology, this is shunt feedback. And the feedback is really just provided by R2. R1 isn't part of the feedback loop. It's out external to the feedback loop. And because of that, things can get a bit confusing. If we concentrate ourselves just on the feedback loop and say, well, I here is really, our input is not this voltage, but the current flowing through that resistance, then all that, then things are all fine. But that's not the way we typically think of this circuit. We think of this as the input, and this is our feedback network, and that's a little bit off, and then our conclusions are a little bit off. Okay, so same deal as before. I calculate the total amount of noise that appears at the output here as a function of my noise source here. Okay. And then I also calculate the gain from the input to the output. I divide, and doing so, I get the input referred voltage noise of this overall circuit here. And the equation is down here. Okay, so the input referred noise of the amplifier was just Vn squared. But the input referred noise of the overall circuit, I deliberately do not use term feedback circuit, because it's really more than a feedback circuit. Right? Feedback circuit plus R1 is Vn times this factor here that includes the gain of the circuit, the closed loop gain of the circuit. And so definitely, I mean, this term is not 1, and consequently the input referred noise of the feedback circuit is different than the input referred noise of just the amplifier right here. And really the reason is that I have an element that is not technically part of the feedback circuit. If you can use a little bit more zoom again, please. Okay, thank you. All right, so then I went through a bunch of examples. I put in different values for the gain. And, well, I mean, if I make the gain -1, then I actually double my noise because of this. Right? Because what really happens is that the noise is amplified by a larger gain than the input signal. Okay? I amplify my noise more than the signal, and consequently, my signal-to-noise ratio is going to suffer. Well, of course. If I increase the gain of the circuit substantially, then that becomes less of an issue. And if I make the closed-loop gain of my circuit less than 1, well, then this is then the noise is a total disaster. Now you may argue, and you're totally right about that. You may argue that who cares about this one? This is not an amplifier. This is an attenuator, and I don't care about this. Well, later, I think I've already alluded to that we are not going to very often use resistive feedback networks, but we are going to use instead capacitive feedback networks. And well, then things are a little different, and we actually can get significant factors where the noise is really enhanced significantly because of this effect here. Okay. So, but the key thing is that if you have such a configuration, be there resistors here or capacitors here, then not feedback itself, but the compound circuit is certainly going to change the signal-to-noise ratio. And as you vary the gain, the closed-loop gain of this thing, the signal-to-noise ratio out here is going to vary also. Okay. And the reason is that there is stuff that is outside the feedback network. All right. The last thing I have about noise is a more complete example. I invite you to perhaps look at it when you get a chance tonight or just before next lecture, so we can go through that quickly. It's a lot of equations, and so it's fairly tedious. I put it in here because I felt that it would help you when you have to solve your own complicated noise example. If you have an example to look at. Okay, I'll see you Thursday.